The 6 decisions of good bin and feeder design. The design of a storage and feed system is a game with gravity, where gravity is the primary force we have to empty a bin or pile. And as designers, we need to ensure that gravity will always be sufficient to keep material flowing. Specifically, we need to ensure that gravity will be sufficient to reliably break the strength of the stored material at the outlet. The future success of your bin can be reduced to 6 key decisions that you need to make. And it is important that you get 6 out of 6 of these decisions right. If you cheat on any of these decisions, you are cheating against gravity, and you are more likely to have a storage and feed system that is susceptible to chronic plugging. Decision 1, flow pattern. What flow pattern are you designing for? Are you designing for mass flow, which is our first in, first out flow pattern, where material slides down the bin walls, where material comes down as a single body, where all the material is in motion? Or are you designing for funnel flow? Funnel flow is our first in, last out flow pattern, where material shears through itself. Or are you designing for expanded flow, where you will combine a mass flow segment with a funnel flow segment? Decision 2, bin shape. The shape of the bin has huge implications on the minimum geometry required for reliable discharge. There are a variety of bin shapes: plane flow, conical, chisel, transition. The minimum geometry, such as minimum angle for mass flow, bridging dimension, and piping dimension, vary from shape to shape. Making a good decision on the bin shape is critical. Decision 3, discharge outlet. If you are designing for mass flow, the discharge outlet needs to be greater than the bulk solid's bridging dimension. Otherwise, the storage and feed system will be susceptible to chronic bridging over the feeder. If you are designing for funnel flow, the discharge outlet needs to be greater than the bulk solid's piping dimension. Otherwise, the storage and feed system will be susceptible to chronic rat holing, which is a particularly dangerous form of plugging. Decision 4, angle of sloping walls. If you are designing for mass flow, the angle of your sloping walls must be sufficiently steep. If you are designing for funnel flow, there is a minimum angle if you want your storage and feed system to self-empty. Decision 5, liner on sloping walls. For many difficult flowing materials, we require a low friction liner in order to get the minimum angle for mass flow to be sufficiently shallow to be workable. In other cases, we require a liner to mitigate wear or the effects of corrosion. Decision 6, effective discharge area. If you are designing for mass flow, by definition, the effective discharge area of the storage bin must be the same as the outlet. Remember the definition of mass flow. The entire mass of material in the storage bin comes down as a single body. All of the material in the storage bin is in motion, and the only way that you get that is if material is emptying equally from the full length and width of the storage bin discharge outlet. If you are designing for funnel flow, the effective discharge area needs to be greater than the bulk solid's piping dimension. Gravity is indifferent about the physical opening of the outlet of your storage bin or slot under your pile. Gravity only cares about the actual area through which material is flowing. The bigger the effective opening, the more stress that gravity places on the material at the outlet. Effective discharge area has everything to do with the behavior of the feeder, so select your feeder wisely. To learn more about why bins plug and the theory that underpins good bin and feeder design, visit the KamengoU website and download our white paper.